Okay, good morning, everyone.
Right.
Good morning. In the last class, we had discussed about uh, Lewis structures and formal charge, right? Lewis structures and formal charge. So, what's the equation to find out the formal charge? Anyone? Emmeline, can you tell me?
Ma'am, I was not there in the last class.
Okay, fine. Alentina?
Total number of valence electrons in a free atom minus total number of ion bonding electrons minus half total number of bonding electrons.
Yeah, half into total number of bonding electrons. Okay. So we have completed the Lewis structures with this formal charge of ozone, right? Now we are going to discuss what's the importance of this formal charge, okay, or how it is related to Lewis structure. So this is the equation to find out the formal charge. Formal charge is equal to total number of valence electrons in the free atom minus total number of non-bonding electrons, that is lone pair. In Lewis structure, we will represent this lone pair as dots, okay, minus half into total number of bonding electrons. So in each bond, there will be 2 electrons. So in this way, you can able to calculate the formal charge. So this formal charges, it will help in the selection of lowest energy structures from a number of possible Lewis structures for the species. We can draw different kinds of Lewis structure for each molecule, right? From that different Lewis structures, we can able to select the proper one. For that, we will connect it with the formal charges. So this formal charges help in the selection of lowest energy structures from a number of possible Lewis structures for the species. So using this from the Lewis structures, using this formal charge, we can find out the proper lowest energy structure from the possible number of structures. So that's the importance of this formal charge in Lewis dot structures. Okay, and the lowest energy structure is the one with the smallest formal charges on the atoms. I told you the lowest Lewis structure can be selected. That is the important or the main Lewis structure. So the lowest energy structure, it is the one with the smallest formal charges on the atoms. Which structure has the least value for the formal charge on the atom? It will be considered as the lowest energy structure. So I will repeat the point again. This formal charges that notes the actual charge, but the charge assigned to each atom in a molecule. Okay, using the previous equation. So this formal charges help in the selection of lowest energy structure from the possible structures. And the lowest energy structure is the smallest formal charge on the atoms. This is clear, children? Yes. Okay. Niranjan, can you please read the points?
Yes, ma'am. Formal charges help in the selection of lowest energy structures from a number of possible Lewis structures for the species. The lowest energy structure is the one with the smallest formal charges on the atoms.
Yes. And in the case of this formal charges, okay, formal charges, that is related to the pure covalent nature of bonding. Okay, pure covalent bonding. What is covalent bonding? That is sharing of electrons, right? Here, this formal charge is also related to pure covalent bonding. That means the equal sharing of electrons between the two atoms in a molecule. So this term formal charge, it will related to pure form of covalent bonding. That is the equal sharing of electrons to the atoms present in a molecule. Clear? This is clear, children? Yes. So So next we are moving to the limitations of octet rule. We have learned that in the case of octet rule, these atoms or elements, they were involved in chemical bonding to attain stability, right? In the case of covalent bonding, they will share electrons and attain stability by completing their outermost shell, right? They will attain stability by completing their outermost shell through chemical bonding, isn't it? So after chemical bonding, the number of electrons in their outermost shell should be complete. But here now we are going to discussing about the limitations of this octet rule. There are some compounds, they will not have this outermost electron contains 8 electrons after the chemical bonding. So it is considered as the limitations of octet rule. Okay, according to octet rule, after chemical bonding, each atom will get 8 electrons in their outermost shell. Right? That is octet rule. But here we are going to discuss the limitations of this octet rule. All of you, please switch on your videos. Okay, so the limitations of the octet rule. First point, the incomplete octet of the central atom. Okay, incomplete octet of the central atom. Here, the number of electrons surrounding the central atom, it is less than 8 in some compounds. The examples are lithium chloride, then beryllium hydride, etc. Here, the total number of electrons surrounding the central atom after the chemical bonding, it is not 8. So it will consider as a one limitation of this octet rule. We can discuss the first example, that's about lithium chloride, LiCl. You know that in the case of lithium, its configuration is 1s2, 2s1, right? 1s2, 2s1. So when they are bonded with chlorine, look at the configuration of chlorine. 1s2, 2s2, 2p6, 3s2 and 3p5, right? 3p5. So both this lithium and chlorine requires one more electron to complete their outermost shell, right? So they will share one electron with each. Lithium and chlorine will share one electron. That's okay. But in the case of lithium, after this chemical bonding, when you look at the total number of electrons in the outermost shell, it is only 2, right? It is only 2 that involved in bonding. In the case of chlorine, it's okay. It has 2 electrons that can be shared and the remaining can be here 1, 2, 3, 4, 5, 6. But in the case of lithium, only 2 electrons are there. Right? According to octet rule, when some elements, they were involved in chemical bonding and their outermost shell will be 8 electrons after the chemical bonding. But here, lithium, beryllium, etc. are the exceptions. Okay, so the first point, the incomplete octet of the central atom, and the examples are lithium chloride, then beryllium hydride, etc. In the case of beryllium, also same thing. 1s2, 2s2. That's the configuration of beryllium, right? 1s2, 2s2. And in the case of hydrogen, it is 1s1. 1s1. So here, there is no sharing of electrons take place. This 2 hydrogen atoms there, so beryllium will donate the 2 electrons, right? So after the formation of a chemical bonding, this beryllium will not get 8 electrons in their outermost shell. They will only get 4 electrons. So due to this reason also, it is not considered, or we cannot completely accept this octet rule. So it's the first point, the incomplete octet of the central atom. The number of electrons surrounding the central atom is less than 8 in the case of lithium chloride and beryllium hydride. One more example you can write, that is BCl3. So here it is 1 electron and 6 valency. In the case of beryllium, it's 2. Then in the case of boron, it's 3. That's the valence electrons present in lithium, beryllium, and boron. Clear, children? So there are certain exceptions in the case of this octet rule. That's it. Here we are considering both types of bonding, ionic bonding and covalent bonding. Okay. Then the second point, that's about odd electron molecules. Odd electron molecules. In molecule with an odd number of electrons, odd number of valence electrons like nitric acid, NO and nitrogen dioxide, this octet rule is not satisfied for the atoms. Okay, we can draw the Lewis structures of these molecules, then it will be clearly understood. Okay. So we can start with, have you completed this point, children? Second one? First you copy this second point, then we can do one example. In molecule with an odd number of electrons, that is valence electrons considered as odd, like nitric acid, NO and nitrogen dioxide, octet rule is not satisfied for the atoms. Normally, when we draw the Lewis structure, after drawing the Lewis structure, when we count the total number of valence electron for each atom, it will be 8, right? But here it will be different. Have we completed? Second point. Adulya, yes or no? Finish, right? Okay. So we are moving to the example of 1 minute, children. NO. Okay, NO. So now we are going to draw the Lewis structure of this NO. So first step, find out the total number of valence electrons. In the case of nitrogen, how many electrons are there in the outermost shell? Nitrogen. Yeah, it's 5 and oxygen is 6. So 11. So here the total number of valence electron is odd number, right? 11. But in the previous all examples that we draw for the Lewis structures, they are even numbers. Did you notice that? The previous examples, carbonate ion, then carbon monoxide, nitrate ion, ozone. In all these cases, the total number of valence electron is even. But here it is odd number. Now we are going to draw the skeletal structure, okay? Nitrogen, then oxygen. Then we can draw the single bond between nitrogen and oxygen. So out of 11, 2 electrons are utilized for this single bond. So remaining 9 electrons, okay? Then we can draw the remaining electrons as lone pairs. So here it's 1, 2, then 3, 4, 5, 6, right? So then only one remaining, that's for nitrogen. This is the second step. We draw single bond, then the remaining 9 electrons is represented as lone pairs. 1, 2, 3, 4, 5, 6, then 7. Sorry, wait. 7, then, yeah, it's 9. Along with this board, there are 9, sorry, 1, 2 here, total 11 electrons, right? Then 1, 2, 3, 4, 5, 6, 7, 8, 9. Right? 8, 9. So in the case of oxygen atom, when we count the total number of electrons, it will be 8. 1, 2, 3, 4, 5, 6, 7, 8. But in the case of nitrogen, it will be 1, 2, 3, 4, 5. So here we are shifting this pair of electrons between nitrogen and oxygen. Okay. Then it will be double bond. Oxygen. Then here 1, 2, 3, 4. Remaining 3 electrons are here. Then you can count the total number of valence electron in each atom. In the case of oxygen, it will be 1, 2, 3, 4, 5, 6, 7, 8. 8 electron. Okay, then we are moving to nitrogen. In the case of nitrogen, 1, 2, 3, 4, 5, 6, 7. Only 7 electron. So here the octet rule is not satisfied in the case of nitrogen. That's why it comes under the limitation of octet rule. Clear, children? Even after shifting this electron pair between this nitrogen and oxygen, we cannot able to create 8 electron in its outermost shell. That's why this one comes under the limitation of octet rule. The same thing occurs in the case of NO2 molecule, nitric acid, etc. So that's the second point. This is clear now? According to octet rule, after the chemical bonding, the total number of valence electrons for each atom will be 8. But here, this is an exception. Have you completed this one? All of you? Yes. Wait. So that's the second point. In molecule with an odd number of electrons like nitric acid, nitrogen oxide, then nitrogen dioxide, octet rule is not satisfied for the atom. Same thing in the case of nitric acid, then nitrogen dioxide, etc. Then we are moving to the third point, the expanded octet. Okay, expanded octet. In the case of this one, more than 8 valence electrons around the central atom. Okay, more than 8 valence electrons around the central atom. In the previous case, you have seen that less than 8 electrons, right? When the total number of valence electrons is odd number, then less than 8 electron after the chemical bonding. Here, more than 8 valence electrons around the central atom. This is termed as the expanded octet. Expanded octet. Here the examples given PCl5, then SF6, etc. So here we can discuss the example of PCl5. So first step, you can find out the total number of valence electron in PCl5. Phosphorus, its atomic number is 50. So what about the total number of valence electron? Yes, 3s2, 3p, 3, right? So it will be
5.
5. Okay. Then about chlorine. Chlorine. 7 plus 7 plus 7 plus 7 plus 7. PCl5, right? Then tell me the total number of electrons.
40.
Yes?
40.
Let me check. Wait. 21, 28. Yeah, it's 40. Okay. Now the second step, we will draw the skeletal structure. Okay. Here the least electronegative atom at the center and the remaining the most electronegative atom surrounding this least electronegative atom. So here P at the center, then chlorine surrounded by this. I will draw it in the next page, okay? Then we can form single bond between each one. So out of 40, how many electrons are utilized for single bond? 10 electrons, right? So remaining 30 electrons. Then no need to complete the entire thing. You just look at the surrounding atoms around the phosphorus. How many bonds are there? Phosphorus, 5 bonds, right? In the case of phosphorus, 5 bonds are there. 5 bonds means 5 into 2, 10 electrons. 10 electrons surrounding this phosphorus. So this is another limitation of octet rule. You can draw the remaining electrons. In the case of chlorine, it will be 1, 2, 3, 4, 5, 6. Then 1, 2, 3, 4, 5, 6. 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay, so 5 into 6, that is 30, right? Yes. So you look at the number of valence electron in phosphorus. Five bonds are there. Each bond will share 2 electron pairs. So 5 into 2, 10 electron. According to octet rule, after the chemical bonding, there will be 8 electrons in the outermost shell. Here it is more than 8 electrons. That is considered as the expanded octet. Okay. So these three are the main limitations of octet rule. Okay, children, when we draw the structures of SF6, then H2SO4, etc., the same thing will be happens. It will be more than 8 electron. This is clear about the limitations of octet rule. Mainly 3 points. Yes. First one, the incomplete octet of the central atom. Then if odd number of total valence electrons there will be less than 8 electron. Then in the case of expanded octet, after chemical bonding, more than 8 electrons surrounding the central atom. This is termed as expanded octet. So that's about octet rule and its limitations. Okay. Then some other drawbacks for this octet rule. So now we are going to discuss the drawbacks of this octet theory. So the first point is that we already started this octet rule or chemical bonding with the concept that noble gases do not involve in chemical bonding because they are stable, right? They do not involve in chemical bonding because they are stable. But here now we are going to discuss about certain noble gases that will form chemical bonds with other compounds. So these are considered as exceptions. Okay, some noble gases also combine with oxygen and chlorine. Okay, oxygen and chlorine to form a number of compounds like XCF2, xenon fluoride, then krypton fluoride, XCOF2, Xc for xenon, okay, xenon, that's a noble gas, then Kr, that's for krypton. That's another example for noble gas. So this is another drawback of octet theory. We cannot able to explain the formation of these compounds using noble gases with this octet theory. So some noble gases also combine with oxygen and chlorine to form a number of compounds like XCF2, KRF2, XCOF2, etc. Then the second point is that theory does not account for the shape of the molecules. We know that each molecule has its own shape, right? This octet theory does not explain anything about the shape of the molecules. That is the second drawback of this octet theory. Then the third one, it does not explain the relative stability of the molecules and energy of a molecule. This octet theory does not explain the stability and energy of these molecules. So these three are considered as the drawbacks of octet theory. Children, please switch on your videos. Sanjana, can you please read?
Drawbacks of the octet theory. Some noble gases also combine with oxygen and chlorine to form a number of compounds like XeF2, KrF2, XeOF2, etc. Theory does not account for the shape of the molecules, does not explain the relative stability of the molecules and energy of the molecule.
Okay. Completed. Yes, right? Then we are moving to the next part, that is ionic or electrovalent bond. Okay. Ionic bond or electrovalent bond. In the case of covalent bonding, you know that sharing of electrons take place. Here, transfer of electrons take place. One atom or element, it will donate electron and the other will accept electron. So, when a bond is formed by complete transfer of electrons from one atom to another, so as to complete their outermost orbits by acquiring 8 electrons, that is octet, or 2 electrons, that is doublet, the bond formed is called ionic bond or electrovalent bond. In the case of covalent bond, sharing of electrons take place. Here, transfer of electrons take place. One atom will donate electron and other will accept electron. Which atom donates electron? That will be considered as cation with a positive charge. And which one accept electron? That is anion with a negative charge. So after the formation of this ionic compound, there will be a cation and anion. So when a bond is formed by complete transfer of electrons from one atom to another, so as to complete their outermost orbits by acquiring 8 electrons, that is octet, or 2 electrons, that is doublet, the bond formed is called ionic bond or electrovalent bond. Eva, can you please read the slide?
Yes, ma'am. When a bond is formed by complete transfer of electrons from one atom to another, so as to complete their outermost orbits by acquiring 8 electrons or 2 electrons, is called ionic bond or electrovalent bond.
Okay. So here the electrostatic force of attraction that will hold the oppositely charged ions together. Okay. You know that there is one cation and anion. They are oppositely charged, right? One is positive and other one is negative. Always is like unlike charges, they will attract each other, right? So here it will holds together by electrostatic force of attraction. So that's about ionic bond or electrovalent bond. Shall I move to next slide, children?
No, ma'am.
Okay, then you can tell me whenever you finished, okay?
Ma'am,
Okay. So next one, ionic bonds will be formed more easily between the elements with comparatively low ionization enthalpies and the elements with comparatively high negative value of electron gain enthalpy. So always this ionic bond will be formed more easily between the elements with comparatively low ionization enthalpies. So in the periodic table, can you tell me which group has the comparatively low ionization enthalpy? What's the periodic trend followed by this ionization enthalpy in a period? Is it increases or decreases? Yes.
it increases.
Yeah, ionization enthalpy increases, right? So the lowest ionization enthalpy will be at the left side of the periodic table. Obviously, alkali metals or the group 1 metals. So always ionic bonds will be formed very easily with group 1 metals. They have the low ionization enthalpy, group 1 and 2. Okay, group 1 and 2. And the elements with comparatively high negative value of electron gain enthalpy. Which group has the high negative value of electron gain enthalpy?
Group 17.
Very good, group 17. So always the formation of ionic bond will be very easy in the case of group 1 and 2 with group 17. That is halogens. Alkali metals or alkaline earth metals with group 17, that is halogens. And always these cations are derived from metallic elements. That means group 1 and 2. And this anions from non-metallic elements, that is group 17. And here one exception, that is about the formation of ammonium ion, NH4+. In the case of NH4+, you can see here, this cation, it's from non-metallic element, and this anion from metallic element. NH4+ is considered as one exception. So in the case of all other ionic compounds, these cations derived from metallic elements and the anions formed from non-metallic elements. It is made up of two non-metallic elements, that's why. Ionic bonds will be formed more easily between elements with comparatively low ionization enthalpy and the elements with high negative electron gain enthalpy. That between group 1 and 2 with group 17. Then cations derived from metallic elements and anions from non-metallic elements. Cations, they have a tendency to donate electron and will become positive. This group 1 and 2, do you remember, they are electropositive in nature. They are always ready to donate electrons. In the case of group 17, they are always ready to accept electrons. That's why their electron gain enthalpy is highly negative. Jacob, can you please read the points?
Ionic bonds will be formed more easily between elements with comparatively low ionization enthalpies and elements with comparatively high negative value of electron gain enthalpy. Cations derived from metallic elements and anions from non-metallic elements. NH4+
Is an exception. Okay. Have you completed the slide, children? Yes or no?
Yes.
Yes. Okay, then we are moving to the next one. That's about their structure. Okay, ionic compounds, they are in the crystalline structure. That means they will be in a three-dimensional crystalline structure. Here, the crystal structure of NaCl is represented here. Okay. So, Na plus ion and Cl minus ion, that can be represented in the form of certain spheres. They are arranged in a proper way, in a three-dimensional way, and this crystal structure will be obtained. So, ionic compounds in the crystalline state consist of orderly three-dimensional arrangements, cations and anions. They are held together by, I think it's Coulombic. Just wait. Coulombic force of attraction or Coulombic interaction energies. So they have a different crystal structure. Here the crystal structure of sodium chloride, it is known as rock salt structure. Okay, rock salt structure. So ionic compounds in the crystalline state, it consists of orderly three-dimensional arrangement of cations and anions. They are held together by Coulombic interaction energies. Here you can see, okay, here you can see the Na plus ion and Cl minus ion in this three-dimensional structure, right? And this three-dimensional structure or the crystal structure of sodium chloride, it is known as rock salt structure. So it's clear, children? Ionic compounds, they will exist in the form of certain crystals with different types of structures. That means they will arrange in a three-dimensional way with a proper packing. Okay. So here in the case of the sodium chloride, its structure is known as rock salt structure. Shall I move to the next one?
Yes.
Yes. So a qualitative measure of the stability of an ionic compound, it is provided by its enthalpy of lattice formation. What's the meaning of enthalpy? Enthalpy. It's energy itself. Okay. So here a qualitative measure of the stability of an ionic compound. I told you this ionic compound, it can be in a three-dimensional way with its crystal structure, right? So this stability for maintaining such a crystal structure, it is provided by its enthalpy of lattice formation, energy of lattice formation, and not simply by achieving octet of electrons around the ionic species in the gaseous state. It's not only because of the octet of electrons surrounding the atom, but also it is due to the enthalpy of lattice formation, energy required for the lattice formation. We will learn detail about this lattice enthalpy in the next topic. Okay. So a qualitative measure of the stability of an ionic compound, it is provided by its enthalpy of lattice formation and not simply by achieving octet of electrons around the ionic species in gaseous state. So this lattice enthalpy, it will play a key role in the formation of this ionic compounds. It will be required for the proper stability of this ionic compounds. Mary Angelina, can you read the point?
Yes, ma'am. A qualitative measure of the stability of an ionic compound is provided by its enthalpy of lattice formation and not by achieving octet of electrons around ionic species in
Gaseous state. Okay. Okay, then one more thing, that is about this lattice enthalpy. What is this lattice enthalpy or lattice energy? So lattice enthalpy of an ionic solid, it is defined as the energy required to completely separate 1 mole of a solid ionic compound into 2 gaseous constituent ions. If you are considering NaCl, it's an ionic compound, right? So how much energy is required to split the sodium chloride or NaCl into Na plus and Cl minus ions? It will be considered as the lattice enthalpy or lattice energy. Clear? Lattice enthalpy of an ionic solid is defined as the energy required to completely separate 1 mole of a solid ionic compound into 2 gaseous constituent ions. Clear? That is known as lattice enthalpy. So here in the case of the sodium chloride, 788 kilojoule per mole, that is considered as the energy required for the breaking of the sodium chloride into its ions. Lattice enthalpy of an ionic solid is defined as the energy required to completely separate 1 mole of a solid ionic compound into 2 gaseous constituent ions. Is this clear, children? Okay, then we can discuss the remaining things, bond parameters in the next class. Okay. Any doubt? Anyone? I told you to send the feedback about my class. But I will receive only 3 feedbacks. So what about others? You should send it today itself. Okay. He told you only mention the negatives. Yes, Ahan. Okay. I will expect today. Okay, children. So let me take your attendance. Just wait.